Okay, this is going to be the fourth video on projectile motion problems. And if you haven't done it yet, I would watch the first three videos and it'll give you a little bit of an idea of how we've gotten to this point. Now, in the first three videos, we had problems where you knew the initial height and you knew the initial velocity, and we're going to vary things a little bit in this problem. So let's run through this and see what it looks like. Let's read through the question first. So let's assume this is assume that you are standing on a 600-foot high cliff. So this is you right here. You're 600 feet up in the air. And your friend is down here in the valley floor. And you want to do this. You're feeling kind of mischievous today. So you want to hit your friend with a water balloon. Now, from his present position, let's assume that he's right here. It's going to take him 8 seconds to get directly beneath you at this spot marked X. So what you want to do is this. You want to throw this water balloon, but you want to make sure that you're not here when it hits him. You want to throw the water balloon so you can run away and be gone when it hits him. So it has to spend at least 8 seconds in the air. So the idea is that your friend and the water balloon are going to arrive at this spot 8 seconds after you throw it. And now the question becomes, at what initial velocity do you have to throw the balloon so that it arrives in time? So we'll actually have a couple of questions to answer on this one, and it looks like this. The first question says this. At what initial velocity must you throw the balloon to time it perfectly so that the balloon arrives at the spot X at the same time that your friend does? So in this case, we know the initial height, and in this case, the initial height, that would be this right here, y sub 0. The initial height is going to be 600 feet. But unlike those previous problems, this time you're going to throw it at some initial velocity. So the initial velocity is equal to what? So a little variation on this problem. So that's what the situation looks like. So with that, let's scoot things down and we'll see what we can do to solve this. So I'm going to move the whole thing down to about right here. And I think I'll get the figure and scoot it down too, just so we can keep things in sight. So we'll move the figure down to here. So that's what our situation looks like. Okay. Now the first thing we've got to do is we'll use the same formula for the general formula for projectile motion that we did in the previous videos. So if you go in your book and you look, this is the formula that we worked with before, and you should find this formula in your book. So the height of an object is given a function by time by this. Is you've got an initial height, you've got an initial velocity, and this will give you the position of an object in projectile motion. Where y sub 0 is the initial height, v sub 0 is the initial velocity, and t is the time in seconds. Now in the previous problems, we knew things like we knew the initial height, we knew the initial velocity. And even in this problem, we know that the initial height here is 600 feet. So y sub 0, this is going to be 600 feet right here. The initial velocity is what we're going to solve for. So let's go ahead and we'll set up the problem down here. Now to do this is you have to think about the problem just for a little bit. You're going to throw the thing up and you know the initial height. You know that it's going to take 8 seconds to get there, so you know time. You want to solve for VO, but what would the height be at that time? Now, we'll ignore the height of your friend. We'll assume that for all practical purposes, that's negligible compared to the 600 feet. So we need to have a reference position when this thing gets to the bottom. So we're going to assume, just like we've always done before, that the reference height right here is y is equal to 0. So the 0 height will be the floor of the valley. So at 8 seconds, both the object and the balloon will be at a height 0. So what this means as far as solving the thing goes is all you have to do is set this initial height equal to 0. So we'll have this. We'll have 0 is equal to, now the initial height was 600 feet. VO, that's what we're solving for. And we know the time is 8 seconds minus 16 times the 8 seconds squared. So it actually turns into a pretty easy problem to solve. Okay, let's go ahead and run through this right here. You'll have 0 would be equal to, this is going to be 600 plus, we'll call it 8 times VO. And if you put this on a calculator, it'll turn out to be 1,024. Now, we'll go ahead and solve this thing for VO. So if you move these two numbers to this side, you'll have 424 is equal to 8 VO. So if you divide, that means that VO, the initial velocity, would be 424 divided by 8, which is going to give you 53 feet per second. So again, fairly easy problem to solve. So, and what this is, again, this is a positive velocity, which means that you're going up. So you'll actually throw the balloon up at 53 feet per second, and you're going to throw it up. Just remember, positive velocities go up, negative velocities go down. So now you know the initial velocity. So again, using calculus, this actually turns out to be a fairly easy thing to solve. Okay, now let's take a look at that second question. So we'll scoot down to right here, and I think I'll move that figure on down a little bit too. So we'll move the figure down, say, to right here where we can see it as well. Okay, now the next thing is this, like we've talked about before, if you're interested in velocity, well, remember, velocity is the rate at which position is changing. So velocity is the derivative of position. So what we're going to do now is we want the formula, but we'll have to rewrite it with the things that we know. So starting with this formula, initially we did not know the initial velocity, but now we know what it is. The initial velocity is going to be 53. So the first step here is to go ahead and rewrite that formula. So this is going to be y is a function of time. And all I'm going to do is rewrite this formula with the things we know in it. So the initial height was 600 feet. You now know that the initial velocity is 53 feet per second times t minus 16 t squared. So you've got the initial position. Okay, let's scoot down a little bit. Now again, we want the velocity. Velocity is the derivative of position. So the first thing we'll do is find the velocity equation. This is the position equation. We want the velocity equation, and that's going to be y sub y prime, and just find the velocity of this thing. Now this is a constant, so it goes to 0, and this will become 53 minus 32t. So this is the velocity equation. So that was velocity. This is going to be position right here. Okay, so you want to know what's the velocity at 8 seconds. So just evaluate the velocity equation at 8 seconds, and you'll have the velocity that it will hit your friend at. So minus 32 times 8, and that's going to give you negative 203 feet per second. So again, it turns out to actually be a pretty easy problem. So we'll scoot back up just a little bit where we can see it. So to find the initial velocity occurs when the height is 0, because you know the initial height and you know the initial time. So solve the first part of the equation, and that will give you the velocity. So you're actually going to wind up having to throw this thing up at 53 feet per second. Then it goes up, comes down, and when it hits your friend, it's actually going to be going down. And when it hits your friend, it'll be going negative 203 feet per second. So again, calculus makes it pretty easy. Now, just for a little variation, let's do this. We'll actually work this problem a second way. On this problem, you had 8 full seconds to keep the balloon in the air before it hits your friend. Now, let's do this. Let's change the problem, and assuming rather than having 8 seconds, you only had 3 seconds. So you've got a lot less time for the balloon to be in the air before it hits your friend. Let's see how that's going to vary the problem. So we'll start with everything else being exactly the same. So let's take a look at that, and we'll rework the problem again with the time being 3 seconds. So we'll go back to here. Let's go back to here, and what we're going to do is make this be 3 seconds here. So we'll change it from 8 seconds to 3 seconds, and we'll change this from 8 seconds to 3 seconds. And what effect will that have on the problem? But again, exactly the same thing as far as working it out goes. Now, first of all, we use the same formula, so we'll go ahead and put that formula on here. So there's going to be the formula, and let's run through the problem again. And it will change. The question is still, what is that initial velocity if you only had 3 seconds? So we'll scoot down to here, and again, I'll move the figure down where we can keep that in sight, and figure comes down here. Okay, so now the initial height is still 600 feet, so you're going to have 600 feet for the initial height. And the question again is still, what is this initial velocity? So we'll still solve it the same way. The balloon and your friend will arrive at height 0 3 seconds from now. So the idea is, again, set the height equal to 0. It'll be the same process we used last time. So 0 is equal to, the initial height is still 600 plus v sub 0, only this time you've only got 3 seconds. So let's see what effect that has on the problem. 16 times 3 seconds squared. Squared. Okay, so now that's going to give us 0 is equal to 600, and we'll solve this equation for v sub 0. So this would be 3 times v sub 0, and this time you'll have minus 144. So again, solving this, we'll move all the numbers over to this side, and we'll have minus 456 is equal to 3 times v sub 0, and if you divide by 3, you get v sub 0. The initial velocity would be negative 456 divided by 3, and that's going to give you minus 152 feet per second. So that's going to be the initial velocity. Now let's think about this for a second. If you look at the picture, here's what it actually really means, is whenever the velocity is negative, that means that you're throwing it down. It's moving down. Whenever the velocity is positive, it moves up. So an interpretation of this actually means this, is if you look at the picture is not quite right. If your friend's only going to be there in 3 seconds, if you were to walk over and just drop it, it wouldn't get there in time. So to make sure it gets there in 3 times, rather than throwing the thing up, you actually have to throw it down, and you're going to throw it down so that it gets there in time. So you're going to throw it down at negative 152 feet per second. So to make sure it gets there in time, even beyond dropping it, you have to throw it down. So in the first problem, you had lots of time. You had to delay the balloon, so you threw it up. On this problem, you've actually got to speed things up, so you have to throw the thing down to make sure that it arrives there in 3 seconds. And then finally, that last question, how fast is it going to be going when it hits your friend? And again, we'll do the same process that we did last time. Let's plug in the things we know. So now you know both the initial height and the initial velocity. So start with the position equation and write that down. So y is a function of time. The initial height was 600. And now you know that the initial velocity, though, is negative 152 times t minus 16t squared. So we'll do the same thing as we're interested in the velocity. We'll scoot this down, and let's go ahead and move our picture back down as well. So we'll bring the picture down to here where we can see it. Okay, now again, what this is the position equation. You're interested in velocity, so the velocity is the derivative of position, so we'll find the derivative of the position equation. That's a constant, goes to 0. This will become minus 152t minus 30, or pardon me, not a t here, let's get rid of that. Minus 152 minus 32t. So it looks like that. Now, what you want to know is what's the velocity 3 seconds after you throw it? So we'll evaluate the velocity equation at 3 seconds. So this is going to become minus 152 minus 32 times 3. And if you stick that on a calculator, you'll come up with minus 248 feet per second. So it's going to be moving pretty quick when it finally hits your friend. So that's going to be the velocity that it would have if you go right down here. So just before it hits your friend, its velocity is going to be minus 248 feet per second. So an interesting problem in that in the first thing, if you have lots of time, you actually have to throw the balloon up in order to make sure it stays airborne long enough to stay in the air for 8 full seconds. But if you only have 3 seconds to work with, if you just dropped it, it would take longer than 3 seconds to get there. Your friend would actually pass that point while the balloon is still in the air. So ensure that it gets there in time, you actually have to throw it down at negative 152 feet per second to make sure it arrives at the same point. So anyway, there's just a couple more examples of how to use projectile motion, and usually it works out where you'll have a position equation, and then also just remember whenever you take the derivative of position gives you velocity. And then we didn't need it in this problem, but if you needed acceleration, the derivative of acceleration would give you, or pardon me, the derivative of velocity would give you acceleration. So there's just another problem, and notice that really the actual math in this problem is pretty easy when you worked it out. So if you use calculus along with projectile motion, generally it makes the problems not too hard to work out. So I hope this helps you again a little bit on understanding projectile motion problems.